Good afternoon, everybody. I'm going to talk about the application of the constraint methodologies for the assessment of components using the failure assessment diagram approach. So our main focus is on the methods which could help engineers to perform quickly and safely the failure analysis using the results which have been derived so far. I have a co-author who is also here. It's Florian Dittmann. He comes from essentially our institute, but works at the moment for the Karlsruhe Institute of Technology. And he made a lot of within this project. So I will give you a short introduction why we do this. Then I will present or briefly review two methods which are have a similar background but have different solutions for applications, and then I will show you how these methods work for two series of test results. One series of the results is, have been obtained for reactor pressure vessel steel, and the other one was obtained for a high strength steel, which is quite different from the first one. And then I will give you some conclusions. So this is well-known fact that if you measure the fracture toughness of different specimens, you get different results, and the question is how to transfer the data between different specimens, and finally how to use this data for the assessment of, for instance, surface or embedded cracks and components. And you also know well that the reason is for this difference is the local stress field at the crack tip, which affects the plastic zone size and shape, and which also affects significantly the stress distribution in the ligament, and by this way the probability of fracture. This is a diagram from a well-known European project which ended some years ago. And you see here all these specimens or some other specimens, and you see that the results of fracture testing in terms of the master curve transition temperature can be approximated by this equation derived by Kim Bollen. And you have, of course, some scatter, but you see a clear trend, and you can parameterize the fracture toughness using the single parameter, the crack tip, the T-stress, and for instance assess such a low constraint geometry like CCT specimen, or also called MD specimen, using the fracture test data obtained on CT specimens. Of course, it's a convenient approach, but the engineers need something maybe more simple, and which is easily applied to assessing components. And such two methods. Before I start with the methods, I will also briefly tell that beside the T-stress, there are other constraint parameters which can be used to calibrate the specimens or to correlate fracture toughness data on different geometries. You can use the T-stress, the Q parameter. You can use this known already triaxiality factor, or more general approach based on the Weibull stress. And this approach has been then used by scientists to derive engineering methods. And to these methods, I would like to present on the next two slides. The first one has been developed within the R6 procedure, and also within European projects like FITNET and formerly SINTAP. I call it R6FITNET method. This method says that one can use the T-stress or Q parameter depending on the level of plasticity in the ligament. And if you know these values, and T-stress is available already for many geometries, you can simply modify your failure line in the failure assessment diagram, or if you put this term in the left-hand side, you can modify the fracture toughness by moving the assessment point along the y-axis. And this parameter beta depends on the respective constraint parameter, T-stress or Q, on the plasticity level. And you have here additional two parameters, alpha and K, which are available from this study as lookup tables, as coefficient, as functions of the, for instance, strain hardening exponent and the Weibull modulus. So you can easily use this method if you are able to calculate the distress and of course the stress intensity factor and the LR parameter for your component. Another similar approach has been developed in Japan by the group of Professor Minami, and they call it IST method. It comes from the abbreviation for the project they had in Japan. And this method works in a similar way, and with some differences. They traditionally use the CTOD instead of the stress intensity factor or the J integral, and they have derived their beta factor similar to that in the FITNET approach from finite element analysis, also based on the Weibull stress model. And they have different rules how to apply this, how to calculate this parameter to avoid, for instance, material testing, or if you have material data, they have another lookup tables or a way you can derive the constraint parameter. So I will now concentrate on these two methods and apply them to evaluate two sets of data. I already mentioned. First one is for this famous German steel, reactor pressure vessel steel, which has been used in several national and also international projects. From those testing campaigns, there are a lot of test data in this temperature range, and this test data cover different crack geometries, CT specimens of different size, bent specimens with different crack depths, and also CCT or MT specimens. So if this data come from our own investigation on this steel, you see here first the results for CT specimens adjusted to the 25 millimeter thickness. They are all described by the master curve approach. Then we put here additionally bent specimens. They are a little higher than the CT specimens, but they are essentially in the scatter band of the master curve for a CT specimen. Then you see here additionally blue points for shallow cracked SMD specimens. You know that this specimen geometry has a lower constraint, or in other words, slightly negative distress, and this brings these points to a beneficial position, so that they show high fracture toughness. And additionally, we put here results for the MT specimens, and they are distinctly outside the master curve scatter band. So we concentrate in the next slides on these specimens. So first we show how these results look in the failure assessment diagram. You see here altogether I think 7 or 8 specimens tested at 2 temperatures. And those which were tested at minus 120 degrees Celsius are in the conservative or on the safe side. All these results are at fracture loss. And you see that at minus 120 degrees, the fracture is overestimated, and considerably overestimated at minus 90 degrees C. So the assessment by FAT is, in this case, very conservative. If we now apply the R6FITNET approach, and what we need to do, we have to select some value for the Weibull parameter. So one can, of course, do testing, modeling, and define this parameter, but for practical engineers, it's almost impossible to do. So what we do here, we vary m between 5 and 15 and look at the results. So in case of test data at minus 120 degrees, the results move towards the failure assessment diagram, so we reduce the conservatism, and all data are still on the safe side. And at minus 90 degrees, we see that assuming m equal 15, we get non-conservative prediction. So we would conclude from this figure that the value of m equal 10 should be likely the limiting value for evaluation of this set of data using this analytical approach. Now we fix m equal to 10 and compare two methods I reviewed before. So we apply FITNET approach and IST method, and we see they both constraint effect, quantify the constraint effect. The points are all on the safe side, but the position of the points change, and this is likely due to the fact that R6 FITNET and IST have different opinion concerning the constraint effect with increasing plasticity. R6 FITNET includes or predicts larger loss of constraint with increasing plasticity, where the other method doesn't do that. So another set of data, number 2, is available from a former project on the qualification of the Ariane 5 booster. It's a high-strength steel with a yield strength of about 1 gigapascal and with a very low strain hardening. So they have performed a series of CT tests. We use those results as reference fracture toughness. And there were also a lot of surface crack tension tests on semi-elliptical cracks with different depth and different aspect ratio. And if we plot now these results in the failure assessment diagram, we get always a conservative prediction. I intentionally put here additional angle position. So usually if we evaluate the fracture for semi-elliptical cracks, we look at the surface and the deepest point, so the 0 and 90-degree position. I intentionally put here also the 35-degree position, and this triangular are usually the least loaded point along the crack front. Now we apply the constraint approach to these results, and I show first the principle and then the overall overview of the results. So we plot here two test results for two specimens. You see here 0 and 90-degree positions. They are almost identical. If we now apply constraint correction, we get better prediction. We put points closer to the failure line, and additionally including, so we assume in this analysis first the viral modulus equal 5, and if we additionally include this intermediate location, about 35 degrees, we see that for both specimens this is the leading point. This is because the T-stress has a variation along the crack front, and at this position the T-stress has a lower value than at the other two. So, and now I show all the results with constraint correction. You see here for each specimen we have 3 points with constraint correction. In some cases we predict fracture starting at the intermediate position, somewhere here. In some cases we have a fracture predicted at the deepest point. And what one should assume is, or imagine, is the upper bound curve coming from the most loaded point, and you see that we are able to describe all these results in a better way and still in a conservative way, even if some points are below the failure line. But this is the point governing fracture, this one, and so on. So now we look what happens if we change m from 5 to 10. So in this case we get most points in the non-conservative range, so we will do the failure assessment in non-conservative manner. So also in this case we should say something concerning the limited value of the m factor. So, and to summarize, I would say there are 2 engineering methods which allow you or engineers to transfer the testing data from high constraint geometries to components, and both methods seem to provide sound description of the test results. One should, however, consider that some non-conservative results are possible if assumptions are not feasible. So we see that there are some advantages of the R6 FITNET approach. First of all, they use the T-stress as a constraint parameter, and this is a value which can be found in handbooks or can be also calculated rather easily by numerical methods. This method also predicts the dependency of the constraint correction on the plasticity level around R, and this seems to be also feasible. And this method also predicts the possibility for crack initiation not only at the positions where the stress intensity factor is maximum, but also at the intermediate locations where some result from consideration of the distress distribution comes up. And still there are some uncertainties in the applicability of this method, and first one is that we see that results can be strongly dependent on the variation of the Weibull modulus. So a value of 5 to 10 could be said to be limited value for some material groups, maybe depending on the material strength. It's important, I think, to say, because in the literature, if you look also for reactor pressure as well, steel, you often find M values in the range of 20 to 40, and this would be definitely too much in case we have considered. And also, there are still some uncertainties in the application of these methods for the cases where we have a high stress component parallel to the crack front. The issue of out-of-plane constraint, and I think in such cases this method should be maybe not applied without validation. So thank you for your attention, and question please.